Assalamu alaikum. My name is Armagan Anjum. I am a research officer from Department of Orthotics and Prosthetics, GC University Faisalabad. Today I am going to discuss about the second part of Principles of Fit and Alignment. Overview. In the last presentation, we have discussed the definitions of fitting and alignment, joint characteristics in different planes, as well as alignment of orthotic joint in frontal plane and effects of malalignment in frontal plane. In this presentation, we will discuss about the alignment of orthotic joint in sagittal plane, effects of malalignment in sagittal plane, alignment of orthotic joint in transverse plane, and effects of malalignment in transverse plane. In the last of the presentation, we will summarize the joint alignment in a table. Alignment in sagittal plane. Alignment of joints in sagittal plane depend to a great extent on the fit of the shoe, bands and cuff. First joint is hip joint. As we have discussed previously, the main objective of alignment is congruency between anatomical and mechanical joint axes. In case of hip joint, the flexion extension axis of hip joint is considered to coincide with a point 1 cm, which is half inch, to 2.5 cm, which is 1 inch, superior to the apex of greater trochanter. Mechanical axis of hip joint must be placed to coincide with this point, so that the both joint can be congruent. The second major joint is knee joint. As we know that knee joint is a polycentric joint as shown in figure, while nearly all orthotic knee components have a single joint axis. Therefore, precise mechanical and anatomical joint alignment cannot be achieved. Because most of the KFOs are equipped with a knee lock, this discrepancy is of no consequence in walking because knee is locked during walking. While accuracy in mechanical and anatomical joint alignment is more important in the sitting position. The flexion extension axis of the knee joint is considered to be approximately 2 cm, which is 3/4 of an inch, proximal to tibial plateau in the average adult, and at a point that is half of the anterior posterior diameter of the knee, not including the thickness of patella. Mechanical knee joint is placed in this position, but accommodation for comfortable sitting must be made in the band or shell of the orthosis. The third joint is ankle joint. The anatomical ankle joint is considered to pass through the centers of medial and lateral malleoli at the level of distal tip of medial malleolus. The medial malleolus is about 1.5 cm, which is 5/8 inch, to 2.5 cm, which is 1 inch interior to the lateral malleolus because of tibial torsion. If congruency between anatomical and mechanical joints is to be achieved, the orthosis must exhibit an equal amount of torsion. Effects of malalignment in sagittal plane. Malalignment in sagittal plane will result in the relative motion and changing pressure patterns between the limb and the band of the orthosis. Greater the range of motion at a particular joint, greater will be the magnitude of relative motion and pressure change. First, I will explain the malalignment of ankle joint in sagittal plane. But before going to the explanation of malalignment, there is some terminologies and background knowledge which is required to better understanding of the explanation. This information is as follows. It is assumed that the stirrups, the shoes, and the foot inside the shoes are fixed, and the anatomical and mechanical axes are parallel. The anatomical axis is denoted by letter A, while the orthotic axis is denoted by the letter O. An imaginary point is denoted by the letter P, represent both points on the calf band and the point on the leg when in the neutral position. This point on the leg will rotate about the anatomical axis, while the point on the calf band will rotate about the mechanical axis. The path of the point on the orthosis and the leg during dorsiflexion and plantar flexion are therefore indicated by the path O and A respectively. Assalamu alaikum. Now we will explain a diagram. There are 4 kinds of malalignment in orthotic joints. One is when the orthotic joints are above the anatomical joint. Second is when it is below. Third, when it is front. and last when it is behind the anatomical joint. Before explaining the boxes, which is motion of band with respect to leg and resultant pressure on the leg, I would like to explain the markings on the diagram. The A denote the anatomical joint, O is the orthotic joint, arc of O is basically the motion of orthotic joint, and arc of A is basically the motion of anatomical ankle joint. P is an imaginary point on the calf band, while the dotted lines showing in front is the basically showing the motion of dorsiflexion, in which foot is stationary and leg is moving forward. Behind you can see the dotted line of leg, and foot is stationary and leg is moving behind, which is the plantar flexion. How we can make this arc? We can make this arc by putting our compass pin on A and our pencil or marker on P and make an arc of A as well as O. Now we will explain the first box, which is the motion of band with respect to the leg in dorsiflexion and plantar flexion. First, in dorsiflexion, as you can see, the arc of O is basically distal or away from the body, then the calf band move away from the body or distally, like mentioned here. In the same way as the arc is distal to the A arc, so the motion of the band will be distal in the plantar flexion, which is written here. Now we will explain the resultant pressure of the band on the leg, and for this we can take only O as a reference, because the pressure is caused when the orthotic joint moves. So we will see only the arc of O, the point of O at posterior side and point of O at the anterior side. We will discuss only these 2 points, as the point of O at posterior side is proximal, while the point of O at anterior side is distal. So when the leg move in the dorsiflexion, the pressure on the anterior side will be distally, and on the posterior side it will be the proximal. Now at the plantar flexion side, the point of O at anterior side and point of O at the posterior side. At anterior side it is proximal, while at posterior side it is distal. So when the leg move in the plantar flexion, the pressure will be anterior proximal and posterior distal on the leg. Here is the second Malalignment condition, in which orthotic joint is below the anatomical joint. As I already told you about the marking, how they are made and what they mean, I will explain the box below. First is motion of the band with respect to the leg. For this we have to compare the arc of A and O. As you can see, in dorsiflexion and plantar flexion, arc of O is above the arc of A, which means it is closer to the body. So during dorsiflexion and plantar flexion, the band will move proximally in both conditions. Second is resultant pressure of the band on the leg. For this we have to see the points of O at posterior side and anterior side. First I will explain in dorsiflexion. As you can see here, at posterior side it is distal, it is away from the body, while at anterior side it is closer to the body, which is proximal. So when the body moves in dorsiflexion, the pressure on anterior side will be the proximal and posterior side it will be distal. And reversal is the case in the plantar flexion. As you can see here, the arc of O, at anterior side it is distal, while at posterior side it is proximal. So when body move in plantar flexion, pressure will be anterior distal and posterior proximal. Here is the third condition of malalignment, in which orthotic joint is in front of the anatomical joint. It is quite different from the previous two, as the band not only move proximal and distal, but also move in a tilted position. For determining the position of band with respect to the leg, we have to consider the arc of O and A. As you can see, in dorsiflexion, the arc of O is above the arc of A, which means during dorsiflexion the band will move proximally as written here. During plantar flexion, as you can see, the arc of O is below arc of A, which means during plantar flexion the band will move distally as shown here. For the pressure distribution, first I read the box. In dorsiflexion, the pressure will be anterior distal and posterior proximal. For this, consider my finger as band end, while my finger is anterior end and my thumb is posterior end. When during dorsiflexion, the band moves proximally and tilted like this, because dorsiflexion is forward motion. As my finger comes down while my thumb comes up, so the pressure at anterior side will be distal and posterior side it will be proximal as written here. For plantar flexion, as it is motion of leg behind posteriorly, so the band will move distal, mean below, and tilted like this, which means my finger is above while my thumb is below, which say that the pressure at anterior end will be proximal and posterior it will be distal as I corrected here. In the last condition of malalignment, in which orthotic joint is behind the anatomical joint and it is a reversal of case when the orthotic joint is in front of the anatomical joint. As you can see, in dorsiflexion the arc of O is below or distal to arc of A, which means during dorsiflexion band will move distally. In plantar flexion, you can see arc of O is above the arc of A, which means during plantar flexion the band will move proximal as written here. For pressure distribution, the pressure in the dorsiflexion condition will be anterior proximal and posterior distal. For this, consider my finger and thumb as band end. Finger will be anterior end and thumb will be the posterior end. As during dorsiflexion, as the band moves distally downward and tilted like this condition, because it is reversal to the front case. As you can see, the finger is above and the thumb is below, which means the pressure on anterior side will be proximal and as posterior side it will be distal as written here. For plantar flexion, the band will move proximally above and tilted like this. As you can see, my anterior side or my finger is below, which means the pressure on the anterior side will be distal and pressure on the posterior side is proximal as I corrected here. You can exercise it at home by using compass or D, so you can better understand all this condition of malalignment. Thank you. Malalignment of knee joint axis in sagittal plane can generate pressure on the limb. Before we go to explanation of malalignment in sagittal plane, there is some information that is required and will be used in the explanation. The information is as follows. The orthotic knee joint is assumed to be a single joint axis, and the leg and the portion of the orthosis below the knee assumed to be fixed. The anatomical axis is denoted by a blue spot, while the orthotic axis is denoted by the red spot.
When the mechanical axis is situated posterior to the anatomical axis, the thigh strap moves proximal and anterior during flexion and distal and posterior during extension. When the knee is flexed, the leg experiences pressure at the posterior calf and the posterior thigh. Here is a demonstration of the previous information. When the mechanical joint is situated anterior to the anatomical axis, the thigh strap moves distal and posterior during flexion and proximal and anterior during extension. When the knee is flexed, the leg experiences pressure at the anterior calf and anterior thigh. Here's a demonstration of the previous information. When the mechanical joint axis is situated distal to the anatomical axis, the thigh strap moves proximal and posterior during flexion, and distal and anterior during extension. When the knee is flexed, the leg experiences pressure at the posterior calf and the anterior thigh. Here is a demonstration of the previous information. When the mechanical joint axis of the KFO is situated proximal to the anatomical axis, the thigh strap moves distal and anterior during flexion, and proximal and posterior during extension. When the knee is flexed, the leg experiences pressure at the anterior calf and the posterior thigh. Here's the demonstration of the previous information. When the mechanical joint axis of the KFO is situated in exact alignment with the anatomical axis, the KFO and leg segments move together. The straps stay in the same location on the thigh and apply appropriate pressure both in flexion and extension. Here's a brief demonstration of the previous information.
Alignment of orthotic joints in transverse plane. Hip joint. With few exceptions, orthotic hip joints permit motion in sagittal plane only, controlling abduction-adduction as well as transfer rotation of the limb. The orthotic hip joint axis is normally placed parallel to the axis of knee joint. Knee joint. The knee joint axis serves as a reference line for the alignment of all lower limb orthotic joints in transverse plane. The reason of choosing the knee axis rather than line of progression is a practical one, because when there is a rotational deformity in the limb, the line of progression will change while the knee axis remains constant. The knee axis, on the other hand, can be easily determined when the knee is moved through a flexion range of 90 degrees. This axis is perpendicular to the plane of motion of the shank and is approximately parallel to the plane of popliteal area when the knee is flexed to 90 degrees. The amount of tibial torsion, which is rotation of ankle axis with regard to the knee axis in the transverse plane, and the degree of toe out can be then related to knee joint axis. Ankle joint. Normal tibial torsion serves to align the anatomical joint so that its motion is compatible with the anterior lateral motion of the center of gravity. If the ankle axis is not perpendicular to the direction of motion of center of gravity, compensatory motion in the subtalar joint will permit the motion of leg on the foot in the direction of center of gravity. Conventional orthoses do not provide motion corresponding to the subtalar joint. Thus, correct location of mechanical ankle axis is great importance. To achieve its proper location, the mechanical ankle joint must be aligned in accordance with the amount of external rotation of the anatomical joint. This is especially significant with free motion ankle joint are used. A common error is to relate ankle joint placement in transverse plane to toe out. While toe out may be defined as the relationship of long axis of foot to the line of progression, that is approximately 15 degrees as shown in the figure on your left side. However, the amount of toe out may be influenced by several other factors than the normal torsion of tibia, which include rotational deformities of limb such as genu vera and valga or coxa vera or valga. Furthermore, the ankle joint axis is normally rotated externally 10 to 20 degrees from the line perpendicular to the long axis of the foot as shown in the figure on your right side. Therefore, ankle joint placement will be inaccurate if it is solely related to the degree of toe out. Toe out. Toe out does not bear a constant relationship to the tibial torsion, since some other factor, as discussed in the previous slide, may influence the degree of toe out without affecting the position of ankle axis. The measurement and accommodation of toe out in orthosis, therefore, must be treated separately from that of the tibial torsion. Effects of malalignment in transfer plane. Hip joint. Internal or external rotation of mechanical hip joint causes the limb or orthosis to rotate internally or externally. It causes undue pressure of the pelvic band on the pelvis as hip is flexed. The second joint is knee joint. During ambulation, the rotational malalignment of knee joint is of little consequence, since the knee is ordinarily locked during ambulation. In sitting position, such malalignment results in uncomfortable pressure. Frequently, knee joint axis malalignment in transfer plane results from the failure to accommodate the patient's toe out. Ankle joint. If mechanical ankle joint is parallel to the knee joint axis in transfer plane, the orthosis will tend to move in the direction parallel to the line of progression during transverse. This is inconsistent with the normal gait pattern in which the tibia and all suprastructure move in anterolateral direction from heel strike to mid-stance. Adverse effects of insufficient external rotation of the orthosis. There will be pressure concentration on the lateral surface of the foot as the normal tibial torsion is blocked. Inversion deformities of the foot and ankle, stress on the knee accentuated by undue torsion of the tibial shaft, patient fatigue due to the binding between anatomical and mechanical ankle joints, increased wear of the orthotic joint. Toe out. If the patient has excessive toe out which is not accommodated in the orthosis, the effects will be as follows. Sitting discomfort with the orthosis due to the external rotation of whole orthosis, various attitude of the foot when the patient sits due to the compensatory motion of the septalar joint. In this slide, there is a summary table of the joint alignment in which hip, knee and ankle joint alignment in frontal, sagittal and transverse plane is shown. Thank you for listening.